When a spanning set of a vector space is as small as possible, we call it a basis. We call the number of elements in the basis the dimension of the vector space. These are possibly the most important concepts in linear algebra. So we call a spanning set of a basis, we call a spanning set of a vector space V a basis if it's linearly independent. And we call the number of elements in a basis the dimension of the vector space V. In a finite dimensional vector space, linearly independent and smallest possible mean the same thing. In an infinite dimensional vector space, well, two different sets can have infinite cardinality, but only one might be linearly independent. So that statement is only true in finite dimensional vector spaces. So, for example, the dimension of Rn equals n because one natural basis is all the vectors with zeros and ones and the one appearing in all possible different positions. So there's n vectors there that make a basis for Rn. The dimension of m by n matrices with real entries is m times n for about the same reason. A natural basis is all the different m by n matrices we can make with a 1 in a single position and zeros everywhere else. So we put the 1 in the 1, 1 position and the 1, 2 position, etc. Then there's mn different matrices that are going to have a single 1 in it, and they form a basis. Now if we look at polynomials in X with real coefficients, that is an infinite dimensional vector space. And a natural basis is 1x, x squared, x cubed, etc. All the different powers of x, there's infinitely many of them. Now if we let pk r be the subspace of polynomials in X with real coefficients, consisting of polynomials of degree less than or equal to k, then this space has dimension k plus 1 because a natural basis is 1x x squared up to x to the k. So we've got k plus 1 powers of x here, because 1 is the 0th power, so that's k plus 1 total, which is why we have dimension k plus 1. And we learned that in Rn, if we have more than n vectors, it's got to be a linearly dependent set. And that's true for vector spaces in general, not just Rn. So if the dimension of a vector space equals n, then any collection of, let's say, m greater than or equal to n, so more than n vectors, is a linearly dependent set. So to prove this, let's suppose the dimension of V is n. And let's let V1 through Vn, little v1 through Vn, be a basis. Now let's choose m vectors u1 through um and write each in terms of this basis. So then we have something like u1 equals a11 v1 plus a12 v2, etc., plus a1n vn, because there's n elements in the basis. And then u2 equals a21 v1 plus a22 v2, etc., a2n vn. And we'll have m equations. Um equals a m1 v1 plus a m2 v2, etc., up to a mn vn. Now I claim that I want to show that these are linearly dependent because there's too many of them to be linearly independent in this vector space. So I claim that u1 through um are linearly dependent. So u1 through um is a linearly dependent set. In other words, there exist constants, scalars, C1 through Cm, not all 0. Satisfying C1U1 plus dot 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 plus CMUM equals 0. So there's some non-trivial linear combination of U1 through UM that equals 0. So to see this, let's consider the system of equations that we get just by plugging these expressions for u into this equation. So that would be C1 times A11V1 plus A12V2, etc., up to A1NVN plus C2A21V1 plus A22V2, etc., A2NVN plus CM AM1V1 plus AM2V2 plus AMNVN equals 0, equals 0V1 plus 0V2, etc., up to 0Vn. So this is the 0 element of the vector space. Now, if we compare coefficients of VI on both sides of the equation, so I is going to be all the numbers from 1 to n. So we'll compare coefficients of V1 on both sides, then coefficients of V2 on both sides, all the way up to comparing coefficients of Vn on both sides. We get a linear system of equations. A11, A21 up to AM1 in the first row of the matrix. So it's going to end up being these coefficients transposed, because if we're looking at coefficients of V1, they're A11, A21, A31 up to AM1. We're setting this equal to 0, so we're going to have n different equations. Each equation is going to have m different coefficients in it. So here's our first equation with A11 through AM1 equaling 0, and then A12, A22 up to AM2 equaling 0, and then finally A1n, A2n up to AMN. So this equation, this describes all the relations between the coefficients that we have set up in this equation, comparing coefficients of V1, then V2, then V3, etc. Now this matrix right here is an n by m matrix. The system has an m by n matrix with m greater than n. So that means that when we row reduce, the resulting row echelon form matrix has some columns not containing a leading 1. So in other words, some free variables. So that means that the number of solutions is infinite. And if the number of solutions is infinite, that means that 0, 0, 0 up to 0 is not the only solution. And if we can find a solution to this equation where the constants are not only 0, that means that our original set is linearly dependent. So U1 through UM make a linearly dependent set. So if you ever have more vectors than the dimension of the space, it's got to be linearly dependent. So a consequence of this, or a corollary, is that if one basis of a vector space V has n elements, then all bases of V have n elements. The proof is that if you have some other set that you think might be a basis, so any potential basis with more elements has to be linearly dependent by what we just proved, and therefore it's not a basis. So must be linearly dependent and thus not a basis. So the dimension of a vector space is well defined, because not only is there one basis that has a certain number of elements, but every basis is going to end up having that same number of elements, the dimension of the vector space. The end.